In this segment, we'll add a logging system to CodeWorlds, introducing a new design pattern in the process, and we'll do a review of variadic parameters as a side topic. CodeWorlds handles exceptions via a logger class, rather than printing error messages directly to system error. And if we look in CodeWorlds Java itself, we can see that there are logger calls, and right next to each one is a system.error call that shows approximately what the logger call does, and we'll give more details in a bit. Now, direct printing to system error, which, by the way, recall is preferred over system.out for error reporting. Direct printing to it is reasonable enough for a simple academic example, but professional code does exception reporting via a more powerful system. Especially in such applications as web servers, exceptions may arise many times during the program run, and they're usually logged in a file for later examination during debugging. Logged exceptions are the critical information by which debugging is done, and the log entries usually give detailed information on the source of the exception, its severity, the time at which it occurred, and so forth. A good logging system can even be configured to email urgent notices to a system administrator. There are powerful Java libraries for logging, but we're not going to build anything as sophisticated in CodeWorlds. We'll just set up a simple logging system in logger.java. And then we'll illustrate a design pattern in the process. Logging systems generally have a class named logger or something similar. You allocate an object of logger and then call its log method. So we create a logger and then we call its log method. And again, these are typical names. The log method records errors or exceptions. So you might see code like logger equals new logger, and then logger.log, and some kind of printf format log message. Now let's take a look at the logger class in more detail here. Skipping over the static member and getLogger method for the time being, we'll return to those. Let's just read the logger constructor and then answer this question. Look up the documentation for print stream, right there. What exception might be caught in the constructor and what would cause it? And then, for that matter, what type exactly is system.error? And is it compatible with member datum out? What object will out refer to after the constructor, and under what circumstances? An answer for that? Well, print stream is an output stream subclass, as you can see right here in the docs, and it performs formatted output. And if you looked it up, you'll find that system.error is a print stream also, so it's compatible with member datum out. You can construct a print stream with a file name, as we do in the logger constructor here. If that construction succeeds, then out will refer to a print stream that is writing to a file named codeworlds.log. But if it fails due to inability to find the file, it throws a file not found exception, as indicated in the Java docs for that particular constructor. So there's the constructor we'd be using, and it says it casts or throws a file not found exception if we can't get to the file. Now in that case, the catch block in logger points out to system error, which, as you know from earlier lecture, is normally directed to the screen, although it could be redirected. Logger has one instance method, log, and that takes a string argument format and then an argument of the form object ... Now, at this point, if you're not sure what object ... signifies in the log header, we'll do a brief summary, but you're welcome to skip over it if you don't need it. So our summary starts with a question. Look up the documentation for printstream.printf. Choose the version without a locale parameter. That simpler version is the one we're using. Does the parameter list look familiar? Turning from a short pause there. Yeah, let's go look at the printf call. The one we want is this guy right here. And the parameter list, in fact, is just like logs, a string format and an object ... Now this is the same printf we use all the time. System.out is a print stream too. Did you ever wonder how printf could take different numbers of parameters depending on how many format specifiers you put in the format string? How would you declare the parameter list when one call of printf takes, say, 2 ints and another takes 3 doubles? Well, the answer is that you declare printf as a variadic method, one that has an arbitrary number of parameters of arbitrary types. Most languages let you do this one way or another. Java's syntax for variadic methods is as shown in printf and log and in this example here in the notes. The syntax object ... args declares parameter args to be an array of objects, as if we declared it object angle bracket args. But when you call the function, you may pass 0 or more separate object references to args, and they'll all be collected into the one args parameter. So if we call printf thus, with the 2 strings and s1 and s2, then the format parameter gets the 2 strings %s, and s1 and s2 are both put together into the args parameter as a 2-element array. And since it's an array of object, args can, of course, hold any reference type. Question 3, by the way, we might pass elementals like ints to printf, mightn't we? I mean, this could have been I1 and %d, for instance. So how does that work, let's say, with the object array? How would that be workable? Just make the obvious guess. Returning from a brief pause there, the integers or any other elementals would be wrapped in wrapper objects, and those would be passed instead, of course. Now, the interesting question is, how does the called method know what type of objects are in args? It knows how many we've passed by args.length, but what type should it downcast them to in order to use them? It can't tell from the variadic parameter alone. A variadic method always requires some other information to decipher its variadic parameter. And for printf, that's the format string. The format specifiers in that string tell printf what to expect in args. If the format is %s, then printf expects args to contain 2 strings, and it will downcast the args elements accordingly. If we lie to printf and pass it, say, 1 integer, then the format string indicates, if the format string still indicates 2 strings, then we'll get a runtime error out of printf. But, as it turns out, our log method doesn't have to do any downcasting. All it does is pass its parameters on to printf. There's the format and the args, after having first printed a timestamp, which we'll look at in a minute. Now, you can satisfy a variadic parameter like args by passing an actual array to it, instead of separate elements of the array. So log's args parameter can be passed directly on to printf. Now, printing a timestamp, by the way, may seem a bit silly in this version of Code Worlds, which immediately ends after any exception. But a larger application may have exceptions at any time, and will often continue running after catching and logging them. For instance, if the web server hit a missing database record and had to abort a page fetch, the site continues running. And in order to debug it later, you want to know when the problem occurred. So the timestamp printf here uses the format specifier, by the way, %tc, which is for printing a date and a time, and it passes a default initialized date object to fill the specifier. Date objects are default initialized with the current time. So the net result is that this will attach a timestamp and a colon to the head of the log message. And here's a representative example in the codeworlds.log file from a test run that I did. Timestamp and the result of the second printf there. Well, now that we understand how logger works, let's consider how we might use it in the catch blocks in codeworlds. Now, we could, for instance, declare a logger in main like that, and then down in the catch blocks we would do the printf in effect by typing logger.log like that. Declaring the logger in main works fine if the only log calls we need are in main, where the logger variable exists. But in a large application, many different points in the code may want to post a log message, either in response to exceptions or for other purposes like debugging information. Let's say, for instance, that we'd like to log a message every time a herd animal finds a new leader. Put a little log call in here. Now, we don't want to create a new logger for each herd animal, because the logger constructor reopens the codeworlds.log file every time it runs, erasing earlier log messages. We really need only one logger object, and it should be used in common by all parts of the code. And we could arrange this by creating a single logger object in main and then passing it to every herd animal, perhaps as a constructor argument. And then every herd animal would keep track of the one and only logger via a member datum and so forth. But that's still pretty tedious. And if we really do want to log messages from lots of places, it won't be just herd animal. We'll be passing that logger object all over the place. We need a better solution. When we need just a single object of a class, which object is widely used, there's a way to let the object be available throughout the code without passing it as a parameter. We have the class in question, logger, track a single object of itself via a static member, like this singleton member here in logger. This is rather like the roster pattern we saw in herd animal, where the class tracked all herd animal objects in a static list member, but here we're tracking just the one logger object. And this design pattern is called singleton. And the typical singleton pattern class has a private static member like singleton, referring to the one and only object of the class, and a public static method like getLogger that returns that one static member. Ignore, by the way, for the moment, the if statement in getLogger. We'll be getting to that one in a bit. To get the singleton object, code anywhere in the application simply calls logger.getLogger. There's no need to pass around a logger reference. Indeed, a typical use, as the one here does, immediately calls a method on the result of the getLogger call. And no logger reference is needed at all. The same code will work just as well, say, in herd animal. Thus, now a UML diagram for this appears in the notes. It has the somewhat odd-looking pattern of the logger class referring to itself. But that doesn't mean every logger object refers to another logger object. Singleton is static, and there's only one logger object, at most, referred to by the class itself. And with that at most comment there, let's go back to the if statement in getLogger that we skipped over before. If a series of getLogger calls, this is question 4, is made during the run of a program, how many times will the singleton equals new logger assignment in that if statement be run, and why? And the answer is only once. On the first call of getLogger, singleton is null, and the assignment occurs. But on all successive calls, singleton is already non-null, and the if is false. Question 5. Describe a scenario in which singleton equals new logger will never be called. The answer, well, if we never call getLogger, then that assignment will never occur. And this would be the case if no log messages were ever needed during the program run, in which case it would make sense not to create a logger. Now, this approach is called lazy creation or lazy initialization of the singleton, because it lazily creates the singleton object only if it's needed, at the last possible moment. You don't have to use lazy creation in the singleton design pattern, but it's pretty common, and sometimes important. For a simple logger, avoiding creation of the singleton if it's never needed is a minor plus. But if the singleton construction involved serious work, like establishing a database or a network connection, for instance, then avoiding that work if it's never needed is a big advantage. And so, in summary, a singleton pattern involves first a class for which at most one object will ever be needed. Then, 2, a static member in the class pointing to the one object instance. 3, a public get method that returns the one object instance. And 4, optionally, lazy creation, by which the get method spontaneously creates the one object instance on the first call.